Okay, guys, back at it again. It's like day 30,517 of the zombie virus. Okay, so we're still in the middle of working with exponentials and logarithms. I have these rules right here, which you guys saw last year. And remember, we reviewed this stuff at the beginning of the year. The one that I'm really concerned with right here is this change of base rule. I know we talked about it. I can't remember whether it was last year at the beginning of the year. But this guy gives us a method, okay, for dealing with derivatives of general logarithms, okay, log base anything, not necessarily natural log or common log, log base 7, log base, I don't know, radical 2, whatever, okay, as long as the base is positive, we could talk about it. Okay, so this change of base rule. Okay, so this allows us to do some things at times, okay, with these guys. Okay, so if you have a graphing calculator, you can take a log base anything because you can change that base to whatever you want it to be. But if you have just a basic scientific Walmart special, okay, you only have access to natural log and common log. Okay, so this log base change rule gives us a very important tool. Okay, so that might be a little small there, so let me rewrite it. Okay, so we have log base A, and A could be anything, of X. Okay, now let's suppose that A was not A was not Euler's number or 10, so this is not the natural log or the common log where you could use your Walmart special to figure out what it is. Okay, so we can use a change of base rule, and this guy will be equal to log base B of X, and that B could be anything, over log base B of A. Okay, now obviously working on our Walmart specials, we would choose B either equal to E, and that'd take us to the natural log, okay, or we could say B is equal to 10, and that would take us to the common log. Okay, so this guy, if I wanted to keep going with it, I could say, okay, so I could choose E as my base. So log base E is a natural log, so this would be the same as the natural log of X over the natural log of A. Okay, so I could easily take this, no matter what A is, and use this ratio and punch it into my calculator and get a value. Okay, or if I wanted to work with a common log, I could say that's the same as log base 10 of X, which is the common log of X, over log base 10 of A, so that would be the common log of A. And again, okay, you could go to your calculator and find out what value that is. Now you're going to see me use natural log a heck of a lot more than common log. I don't know, maybe it's just out of habit, who knows, okay, or it's what I'm used to doing. Okay, so for instance, let's suppose we had something like this. Let's suppose, I don't know, let me just make one off the top of my head. What if I had log base 7 of 15? Okay, now, in these scientific calculators, I can't do log base 7. And 15, we can't write it as a power of 7 using rational numbers, so I can't even go old school and come up with a value for it. But I need to know what that value is. Okay, so we can go to this base change rule. Okay, and I'm going to use the natural log rather than a common log. And I could say, okay, well, this is the same as log base E, which is a natural log of 15, over log base E, which is a natural log of 7. And then I could punch that into my calculator, and it'll actually give me a value. Okay, so if we go natural log of 15 divided by the natural log of 7, and we are going to get roughly 1.39. Okay, now just so you guys know, it'll work no matter what you do. Okay, so for instance, if I decided, well, I'm going to use the common log, okay, and I say, okay, well, this is the same as log base 10, the common log of 15, over log base 10 of 7, so that's the common log of 7, and I punch that in, and you guys are more than welcome to check that for yourself. So I go common log of 15 divided by the common log of 7, and lo and behold, we get the exact same thing, which obviously should happen. Okay, so this base change rule comes in handy every once in a while, and it definitely comes in handy today. Okay, so we take a look at, what do we do to find derivatives of, just your general logarithms. Okay, it's not a natural log, it's not a common log, it's just any log base A whatsoever. And I left myself a little hint there, and we said, okay, well, why not consider a base change, okay, and go about our business. Okay, so we say, okay, all right, well, I have a habit, once again, of using the natural log. Okay, so I'm going to write log base A of x using a base change and log base E, or natural log. So this would be the same as the natural log of x over the natural log of A. Okay, so it'd be log base E of x over log base E of A. Okay, so we take a look at that. Now notice this natural log of A. Now notice A is a positive number. Okay, it's a positive number. So log base A is a constant. So that means we have a constant multiplier of 1 over natural log of A. So why not just remove that, 1 over natural log of A times the derivative of what remains, and that would just be the natural log of x. Okay, all right, so we have that constant multiplier out front, 1 over natural log of A times, well, the derivative of the natural log of x is 1 over x times, using the chain rule, dx dx. And of course, dx dx is just 1, so I'm just left with the product of these two. And so I would get 1 over x times the natural log of A. And there we go. We got a formula, okay, for taking derivatives of general logarithms, okay? Works no matter what. Okay, so for instance, we've got stuff like this, okay? All right, now you have to account for the chain rule, okay? So rather than using an x here, I use an A, okay? So we would get 1 over, x is now u, so it'd be 1 over u times the natural log of the base times the derivative of u, okay? And obviously, if u is just x, that derivative, we just get dx dx, and that's 1, so it just goes away. But most times, that x is not x, it's some quantity, okay? So a lot of these guys down here, okay? So we just take a look at some of these guys. They're relatively easy to do. Okay, it's just applying a formula once again. Okay, so if we do this first one, okay, we have the derivative, okay, of log, notice that's the common log, log base 10, okay, of x squared plus x minus 12. Okay, so obviously this guy right here, this quadratic, is my u. Okay, so when I take the derivative, I go 1 over u, which is x squared plus x minus 12, times the natural log of the base, which is 10, natural log of 10, times the derivative of u. And the derivative of u would be what, 2x plus 1? And then we just clean it up. Okay, that's it. Okay, so I'm going to get, let's see, 2x plus 1 all over the quadratic, x squared plus x minus 12 times the natural log of 10. All right, now you would all obviously check to make sure that's reduced. Okay, so if we take a look over here, this x squared plus x minus 12, notice that guy factors into what, x plus 4 times x minus 3. Yep, Okay, and so obviously neither of those two factors will cancel with a 2x plus 1, so it is reduced. Okay, so you can leave your answer in this form. Okay, if you wanted to factor that quadratic, that's okay. You could do that as well. It's just not necessary. Okay, so let's see what we got going on the second one. Okay, all right, that was number 1. Here we go on number 2. Okay, we got the derivative. Notice again, we're working with a common log. So it's log base 10 of sine of x. Okay, so again, this sine of x acts as our u. Okay, and we just go right back up here to our rule. Okay, so we get 1 over u, which is the sine of x, times the natural log of a, and a is 10, natural log of 10, times the derivative of u. And the derivative of sine is cosine. Okay, so let's see what we can do to clean this up. Okay, I could write it as cosine of x over sine of x, natural log of 10. Okay, now it depends on who's in the front of the classroom. Okay, some people might say that is an acceptable answer. But notice we have that cosine over sine, okay? And cosine over sine is cotangent. Because remember, sine over cosine is tangent, so cosine over sine is cotangent. So that would be the same as the cotangent of x over the natural log of 10, right there. Now, I would say that second form of the answer is probably a little bit simpler than the first form. Okay, I like this guy better than that guy. But depending on who's in front of the class, you could have a teacher that would accept that. Okay, so let's go down to the third guy. Let's see, what's this guy? Okay, so we're going dx of log base 3 of the cosine of x. Okay, so let's see, cosine of x is my u, and obviously my a is 3. Okay, so when we take the derivative, we go 1 over u, which is cosine of x, times the natural log of the base, which is 3, times the derivative of the cosine of x. And the derivative of cosine is the opposite of sine of x. All right, and then we're just cleaning that guy up. So we get the opposite of sine of x over cosine of x times the natural log of 3. And again, this is just like the previous one. Okay, it depends on who's in front of the class. Okay, you take a look at that guy, and certainly that could be an acceptable answer depending on who's in front of the class. But we know that sine over cosine is tangent. Okay, so I know me personally, I would rewrite this as the opposite of the tangent of x over the natural log of 3. Okay, and I think that's a better form of the answer right there because it's a little bit simpler than the one above it. Okay. All right, so let's see. We got the first 3 done. We got 3 more to do. Let's see what we got going on here. Okay, so let's see. We're on this guy. Let's make sure. I want to make sure you can see all that stuff. Okay, we should be good there. Okay, so let's see. Number 4. Okay, we got the derivative of log base 7 of 10 minus 9x. Okay, so obviously our 10 minus 9x is our u, okay, and obviously our a is 7. Okay, so we take the derivative and we get 1 over u, which is 10 minus 9x, times the natural log of the base, which is 7, times the derivative of u. And let's see, the derivative of 10 minus 9x would just be negative 9. Okay, clean it up. So we get the opposite of 9 over 10 minus 9x times the natural log of 7. Okay, let's see that guy right there. Doesn't look like there's anything we can do there, because really the only thing I could do is if I had a common factor down here of either 3 or 9, I could reduce it with the 9 up there, and I don't have that. So that is about it. Okay, let's see. Number 5. All right, the derivative of log base 2 of e to the x minus 4. Okay, so let's see. Here's my u right there. So we get 1 over u, e to the x minus 4, times the natural log of the base, which is 2, times the derivative of u. So when I take the derivative of e to the x, I just get e to the x. And when I take the derivative of negative 4, I get 0. Okay. All right, so let's see. We get e to the x all over the quantity of e to the x minus 4 times the natural log of 2. And again, nothing, I don't see anything we can do with that. Okay, I would need a common factor of e to the x that I could factor out down in the denominator, be able to cancel with the numerator, and certainly we do not have that. So it looks like that's it. All right, let's see, number 6. Okay, the derivative of the common log, so log base 10, of the square root of x squared minus 9. All right, now this guy is, again, for the most part, it's straightforward. Now the problem we get into is this guy is your u right here. So when you take the derivative of u, then you got to apply the chain rule. Okay, so I say, okay, well, how can we deal with that and not have to apply the chain rule? Well, couldn't I take this expression, this square root, and put it in an exponential form first? And then wouldn't I have an exponent that I could pull out front using my power rule? That sounds like a plan. Okay, so let's see. This is the same as the derivative of log base 10 of x squared minus 9 to the 1/2 power. Okay, so that 1/2 comes out front and becomes a constant multiplier. So I get 1/2 times the derivative of log base 10 of x squared minus 9. And now when I take the derivative, I don't have to, well, I do have to use the chain rule, but I don't have to use it more than once. Okay, so relatively easy to do. All right, so let's see what we got going on here. Okay, so I get the 1/2 out front times, it's going to be 1 over u, and obviously this guy is my u right here. Okay, so 1 over x squared minus 9 times the natural log of the base, so that'd be natural log of 10. Okay, times the derivative of u, and the derivative of x squared minus 9 is just 2x. Okay, so let's just clean that up. And notice we can reduce this guy because I've got a 2 down below, which goes away with the 2 up above. Okay, so I am left with x over the quantity of x squared minus 9 times the natural log of 10. And that is about all you can do there, okay? Because once again, to be able to reduce it, I would need a common factor down here of x that I could factor out and reduce with the x in the numerator, and I don't have that. Okay, some pretty simple stuff today. You guys make sure, once again, okay, stay safe out there. I miss all of you, and I'll see you again soon.